discussing about two of the temperature transducers. One is resistance thermometers and thermistors. So resistance of a conductor changes when its temperature is changed. This property is used for measurement of temperature. The variation of temperature and T can be represented with the following linear relationship given by the following relationship given as R equal to R0 into 1 plus alpha 1 T alpha 2 T squared. And if you see, this relation is not a linear relation as I mentioned previously, but it's a quadratic equation. Okay, so what are the terms that involve what are the terms that can be defined? So R0 is the resistance of a conductor at 0 degrees centigrade, or alpha 1, alpha 2, alpha 3, alpha n are constants. So the resistance thermometer uses change in the electrical resistance of a conductor when the temperature changes. So the requirement of the conductor material to be used for the thermometers is change in the resistance of the material per unit change there should be as large as possible. That is, the sensitivity should be as large as possible. Resistance of the material should have continuous and stable relationship with the temperature. Characteristic of various materials used as the resistance temperature detectors or RTDs can be shown in this figure. So these materials are platinum, copper, and nickel. Okay, so when the temperature increases, there is an increase in the resistance, and this is a positive temperature coefficient. That is, when the temperature increases, resistance also increases. And how it is actually made? So there will be ceramic beads connecting two wires that have been welded at the end, and these ceramic bead separates the rest of the wire until the point of measurement. Okay, so these wires come out and they are connected to the instrumentation circuit. You should always think that this RTD or similar to some compensation methods that we saw in the strain gauges. So they also go into a Wheatstone bridge, and based on the resistance change, and there will be a change in the deflection in the Wheatstone bridge, and the deflection can be calibrated as temperature. Voltage difference can be calibrated as temperature, but the problem is it also has lead wires issues. So based on the length of the wire, the resistance also increases. So for this we use 2-wire compensation technique, 3-wire compensation technique, 2-wire is the normal technique that will cause the resistance problem, 3-wire compensation technique and 4-wire compensation techniques. So these techniques we have already seen in strain gauges. Similar techniques are used so that the resistance change is purely due to the temperature change. Okay. So these are some of the tabulations of temperature resistance temperature coefficients and temperature range. So based on different material, the temperature range changes. If you see, the range of temperature that can be operated in a large level is platinum, followed by tungsten, nickel, and copper. And they are also considered based on the melting points of these metals. Okay. The platinum and nickel, copper are most commonly used metals to measure the temperature. The alpha 1 for the platinum between 0 to 100 degrees is 0.004 per degree centigrade. The resistivity of the platinum tends to increase less rapidly at higher temperature than other metal. Therefore, it is most commonly used metal for resistance thermometer. The platinum is the commercially available in the pure form and has the stability over high range of temperatures. So what we do, we similar thing that we discussed in the unit 1. We calculate the temperatures for various things, and for various level of instruments we plot the resistance, and using the resistance we plot resistance in y-axis and temperature in the x-axis, and based on that we will plot the graph. Okay, and this graph will be so what is this graph? This is the you can use the equation of the straight line, that is y equal to mx plus c. What is y? Resistance. X is temperature. M and c are slope and the intercept. You can see something very closely written here. So R0 naught plus R0 naught into alpha theta naught into delta theta, that is this that is the slope value. Okay, so this is the slope value, and the input temperature can be written in this form. So that is R theta equal to R theta at 0 degree centigrade plus 1 plus alpha, that is resistance temperature coefficient at 0 degree centigrade, plus delta theta, that is the difference in the temperature. Okay, so based on this you can calculate your required temperature, required resistance change at the specific temperature theta. Okay, so this is what they have given there. So or theta naught into slope. So this is the slope value, and this is the intercept value. This is the slope value, and the alpha theta naught can be calculated by this method. This is called linear approximation method. Okay. And there is also another method. So when you wanted to measure for wide range of temperatures, there might be as it was told, the platinum's resistivity changes lesser at the higher rate of temperature. But if you see nickel and copper, there is an asymptotic kind of change in the temperature. What is asymptotic type of change in temperature? So something, you will see something like this when measured at higher temperature. See, it doesn't, it is not linear, but it increases in almost a vertical line. Okay, both for nickel and copper. So then you cannot use a straight line equation, but you can go for a quadratic line equation. Okay, so using this quadratic line equation, which we would have seen the very first, okay, we can determine what is the temperature. Okay, so this is RTD.